Hello everyone. I'd like to introduce our guest, Tom Beckley. You can see his role there, but I'd like to say a word for Cadence just briefly. I've been making microchips with undergraduates and graduates alike for about 15 years, and Cadence is still the premier platform for full custom design, and for many years, the premier platform for digital design as well. So in many ways, their company has had the best technology at solving ridiculous problems. Well, we've enjoyed the presentations from BMWC, and you'll get to meet more folks from the fab side later. The EDA side should never be ignored because we can't do our designs without these folks coming up with the algorithms and software that we use to make them work. So, after that, over to you, Tom.
Thank you. Can you hear me okay? All right. Thanks for the introduction. My goal today is to, how much time do I have? Maybe about 30 minutes? Does that sound right? Yeah, okay. My goal today is to kind of give you a panoramic tour of what's going on in advanced electronics and increasingly how it's moving from semiconductors into full what I would call systems, electromechanical systems. So that's kind of part A, and you'll see that I'll touch on, at a high level, I'll touch on a lot of pieces of what does it mean to design a semiconductor and to design complex electronics. That's part A. Part B is to talk about some of the technology inflections that are unfolding that will impact your careers. And I'll tell you about our company, Cadence Design Systems, and some of the opportunities we have, some of the transformations we're going through, and I'm hoping that as you look at your career choices down the road, you'll consider Cadence as an opportunity. And probably the third thing I'd say is that I started my career, designed my first chip in 1981. I'll talk about that in a minute. Long time ago. It's been an incredible career. But when I look at the world I faced coming out of graduate school in 1981 and the opportunities that you have before you, yours are an order of magnitude greater, in my opinion. I think whether you are choosing an engineering curriculum or maybe even beyond that in the sciences, I think the impact of electronics coupled with software, coupled with mechanical, is really going to be really, really great for you. All right, let's get started. Oops, am I working?
Back here.
There we go. So, a little perspective. When I was 3 years old, there was a junior senator from Massachusetts who came on a train stop through Pontiac, Michigan into Oakland Park. My mother took her 5 kids to see the junior senator, and I was held up at 3 years old by then, who then became President John Kennedy. After graduate school, I went to a company called Harris Semiconductor. It was located in Melbourne, Florida, right near Cape Canaveral. I designed RF and millimeter wave chips. These chips went into space shuttle applications for the most part. For those of you that are starting to look at chips, they were radiation hardened. So they were for space electromagnetic challenges that the space program faced at the time. I was at Harris for a number of years. It's now called L3 Harris. The semiconductor group was sold off and is now part of Renesas. That's part of Japan. But I did 3 startups in EDA. The last one was out of a university in Pittsburgh, Pennsylvania called Carnegie Mellon University. That's where I live. And it was acquired by Cadence in 2004. So I've been with Cadence now for over 20 years. I joined the senior management team in 2010. And I'll share some of those experiences in just a minute. So this is me. I was young once. I can tell you that I have 6 kids. My youngest is 29 years old, so all of you could be my grandkids. I can also tell you this was me in 1981 when I started at Harris. And I started off and I was very fortunate to be surrounded by some very senior RF designers and millimeter wave designers that helped me learn. And that's going to be a hallmark of your career, is to get with somebody who really understands chip design, verification, validation, and learn from them. This is an industry about continuous learning and being surrounded by smart people. One thing I'll say about Harris, you probably can't see this very well, but our employee numbers were our Social Security numbers. So they failed the security test. So I said earlier, it's a great time to be in engineering, but it's also a great time to be in the sciences. And while there is an electronics revolution going on and it's enabling an AI revolution, the truth of the matter is that it doesn't work without a software revolution. And so those have to go hand in hand. So whether you're considering semis, electronics, mechanical, software, we need you. That's the truth of the matter. To the extent that you can cross multiple domains, you will be ever so more valuable. So here are some of the major technology inflections that we see underway right now. And I'll talk about a few things like Moore's Law and heterogeneous design in just a minute. And I'm not going to read these to you, but as you look at them, what I will say is that they are all interdependent. They all require complex semiconductors, advanced node semiconductors, and all of them accelerate and enable AI. Every product is using next generation electronics and next generation software. Now, we live in a world of intelligent products. You have a smartphone, you have smart glasses or VR, you have smart cars, you have smart homes, you have smart rings. The list just goes on. And increasingly, these are interconnected and ever more personal. You use them at home, you use them at work, right? And so it begins at the silicon level, it builds to the system level, and increases as we layer in kind of AI applications across the board. Here's one of the reasons why I think you have great career opportunities. The semiconductor market, in just a few short years, will surpass $1 trillion. When I entered, it was struggling to get into the low billions. Struggling. The systems market, enabled by those semis, will exceed $3 trillion in a few years. It's amazing how big and the electrification that's underway. If you look at an EV vehicle, any guesses at how many semiconductors are in an average EV vehicle?
30?
30. Nope.
500?
Way too low. Yes?
3,000?
Too low. I can't hear you. Oh, not that many. No, on average about 8 to 10,000 today. 35% of the cost of a vehicle today is increasingly by electronics. It'll be 50% probably within 3 to 4 years. Not too many years ago, a decade ago, that percentage, I said it's 35% right now, that percentage was below 10%. Look at the electrification going on. You also see it in your dorm room, you see it in your homes, you see it every place, right? So many opportunities. Now, I wanted to talk a little bit about AI. And certainly in our world, you know, Cadence, I'll talk about Cadence in a minute. We have about 12,000 employees. I would say at least 1,000 of them are working on AI opportunities across all of our design platforms. And so we're in this stage right now that I call kind of Horizon 1, which is kind of the infrastructure build-out for AI. And you see it with the advent of GPUs kind of going into large data centers that are being built across the globe, right? What we know about AI is that it's pretty good at voice synthesis, at audio synthesis. We know it's pretty good at image recognition, right? And so by definition, we've seen kind of unfold kind of what I call is Horizon 2, physical AI. It's the world of drones. It's going to be the world of autonomy, whether it's vehicles or other types of ways of transporting. I see it on the way things are delivered here on campus, right? Probably the biggest one will be robotics over the next 3 to 7 to 8 years. You'll see a little bit of information about NVIDIA sprinkled into this presentation a little bit. I first met Jensen, the CEO, and Chris Malachowski, the two founders, I think it was 1994. They had a struggling company. Believe me, they almost went bankrupt about 4 times. Jensen doesn't talk about that much anymore. They really wanted to revolutionize 3D graphics for gaming and multimedia, right? But then they stumbled onto this world of AI, right? And of course, there was a bit of a perturbation that happened just a couple days ago, right, with DeepSeek, right? My opinion is that's a great thing. That's the software revolution accompanied with the silicon revolution coming together, right? It's inevitable. Whether it's a Chinese company or a US company, I don't care. Anything that makes model training and inference faster and more efficient, I welcome it. You should welcome it, right? Right. The biggest AI market is in the sciences world. This one will be huge and it will transform the universities. My hope is that some of you, 40 years from now, will be up here speaking to another group like this, and you'll be sharing your career and the big trends that unfolded for you and what will be in the future for other students. So let me talk a little bit about Cadence, what we do. I hope you know a little bit about us. You may not. I said we're about 12,000 people. Our revenues this year last year approached about $5 billion. What I like most about Cadence is it's an engineering company for engineers. Our CEO has a PhD out of Carnegie Mellon University, was the fastest graduate ever in ECE at Carnegie Mellon, and we actually shared a thesis advisor. I was much earlier than him, and that's the reason he's CEO is we need deep technologists to kind of lead the company. His expertise is in mathematics and simulation and AI. The reason it's an engineering company is for every dollar revenue we bring in $5 billion a year, a third of them go back into R&D. Now, if you look at most industries, they're well below 10%. So we're sitting around 35% going into R&D. And Wall Street doesn't like it, frankly. When I started at Cadence in 2004, when my company Neolinear was acquired out of Carnegie Mellon, Cadence's market capitalization, the value of the company was about $1.5 billion. Today, it's about $82 billion. So if you think there isn't a technology wave going on, there is. Now we have 26 development sites, 15 years in a row, a Fortune top 100 company. I think we were in the top 10 last year. Consistently shown as one of the most innovative companies. That's probably why when DeepSeek announced, Cadence's stock got hit pretty hard, to be frank. It was meaningless. It really doesn't affect us. Actually, it makes our business better, but the street doesn't understand that. Most people don't understand that. It probably will affect Jensen and NVIDIA. That's the truth. Maybe the number of GPUs needed, which affects the price they can charge for them, will be impacted. Maybe that's healthy for the globe. Maybe not healthy for Jensen, but we all get humbled in this world of technology. The other thing I'll say about Cadence, and I'm really proud of this, is that we are very socially responsible. We actually, as an executive team, meet frequently and talk about how we can decrease our carbon footprint. We have no gender pay gap at Cadence. There's none. There hasn't been one for 5 to 10 years. If you're talented, you get paid well. If you're really talented, you will run large design groups as long as you have the managerial and communication skills that go with it. So we also have a very large foundation. We have a lot of programs underway. Honestly, I think it's a great company. I think you should consider it. You should learn more about it. Hopefully today will help. So one of the things that happened was that when I was elevated to the executive management team, and that was in 2010, my very first presentation to the CEO of the company and to the leadership team was about Cadence moving out of what we call classic electronic design automation, chip, package, board, electronic design and into the world of system design automation, which is layering in all of the mechanical analysis, electromagnetics, thermal analysis, signal and power integrity, computational fluid dynamics for kind of how fluids affect things like turbulence and the like, and air affects turbulence. And so within my group, I changed my roles just about a month ago, but up until the end of last year, I actually had 2,000 engineers in my R&D group. And one of the things we did over the last 6 years was we expanded Cadence from an EDA company to a system design automation company. And the reason I wanted to kind of point that out is it's going to be talked about in this next NVIDIA video that follows. Yeah, thank you.
For nearly 4 decades, Moore's law has been the governing dynamics of the computer industry, which in turn has impacted every industry. The exponential performance increase at constant cost and power has slowed. Yet, computing advance has gone to light speed. Let me highlight some acceleration libraries that solve new challenges and open new markets. The auto and aerospace industries use CFD for turbulence and aerodynamic simulation. The electronics industry uses CFD for thermal management design. This is Cadence's slide of their new CFD solver accelerated by CUDA. At equivalent system cost, NVIDIA A100 is 9 times the throughput of CPU servers. Or at equivalent simulation throughput, NVIDIA is 9 times lower cost or 17 times less energy consumed. Worldwide industrial CAE uses nearly 100 billion CPU core hours yearly. Acceleration is the best way to reclaim power and achieve sustainability and net zero.
So I just threw that in because I wanted you to understand how Cadence is transforming. 7 years ago, 6 years ago, we did nothing in electromechanical design. Today, we're one of the leaders, not only in electronic design, but increasingly in where those worlds come together, which quite frankly is everywhere. Oh, I think we're repeating. Yeah. Here we go. So let me tell you a little bit about the history of semiconductors. And sorry, this is a bit of a passion for me. For those of you that don't know, anybody know what year the transistor was invented? Sorry?
49?
47. Well, actually, probably a couple years before that, but the Nobel Prize was awarded to Walter Brattain, Bill Shockley, and John Bardeen, all of AT&T Bell Labs back then, for the invention of the transistor. But these two guys are pretty interesting too, Jack Kilby of TI and Bob Noyce of Fairchild. Because while these guys were inventing the transistor, these guys were simultaneously inventing the transistor and applications for it that created huge companies. We'll talk more about that in a minute. What I would posit to you is that the semiconductor and the invention of the transistor has probably been the biggest revolution to the history of mankind in terms of improving people's lives. It's absolutely stunning. I know a lot of you have always only lived your world with a cell phone, but for many of us, we didn't have one, and we'll talk more about that in a minute. These guys are really important. This is just a high-level depiction of kind of how does someone build a product like this, right? We'll talk more in detail about this, but it all starts with silicon, right? Silicon is the second most common product or element in nature. The second most. Anybody know what the first most is?
Carbon.
Sorry?
Carbon.
Nope. Oxygen is number 1. Number 3?
Nitrogen.
Nope.
Hydrogen.
Nope. Aluminum. You wouldn't have thought that, would you? Number 4? Iron. Now this is in nature, right? So this is involving the earth, not just the atmosphere, right? So It's amazing. The second most popular element in nature, silicon, is the basis of the revolution for semiconductors. And so with it, there's one thing you kind of see here as we move from EDA, we move into fabbing, and making a semiconductor, and then we kind of package it and we put it in a mechanical system and we end up with a product. The one thing you see is the software revolution that accompanies it every step of the way. So what is electronic design automation, right? Many of you know, of course, it's how do I design? Has anybody used maybe a product called, have they designed anything yet in this class?
So this class is a seminar class, so not yet, but they
Not
do
yet.
have from various STEM backgrounds. We've actually got quite a mix in here.
Okay. So you may hear of a product like Virtuoso, which is massively popular across the globe, probably 90% market share. One of my products, honestly, that I worked on actually started at Harris Semiconductor, literally in the early 80s. And then it was bought by a company that became Cadence, and then developed and then became one of my products yet again later on. But in any event, it's really chip design, the package that goes around the chip, and of course the board that it goes on. And then we have a whole bunch of what we call as IP. And you might think, well, IP is like patents, but in our world it's not. IP is things like embedded memories. IP is things like interface IP. So it might be like Bluetooth, or it might be HDMI or USB. And the reason that companies like Cadence develop that and offer it to other companies, say like a Tesla, is because every product needs it, right? So it doesn't differentiate your product. So you don't want to spend a lot of time and money on it, so you license it for a company like Cadence. We see on your left-hand side, a chip design. See this is kind of a digital chip design. You'll learn more about this as you go in. That has to go into a package to protect the silicon. Remember that second most common element. And then that package goes on and is interconnected with other semiconductors on a printed circuit board. I know this is, like I said, 101. Let's just spend a minute on the economics of semiconductors. Why did I call it a miracle story? So here's another picture. You might recognize, there's Bob Noyce again. This was Fairchild. This picture was taken in 1966, in fact. And on the far left here, a guy named Gordon Moore. My thesis advisor worked for Gordon Moore as an academic. Later went on and wrote a simulation program called SPICE. In any event, you'll learn that later on. There's a Cadence program called Spectre that's very popular based on that SPICE work. These two guys, actually three of them, went on and in 1968 formed a very famous company. Anyone know what it is? Yeah, Intel, right. They formed Intel. Now, Gordon Moore came up with something that it's not a law, but it's called Moore's Law. But basically it said that using silicon, that every year, and it started with every 12 months, the number of transistors would double every year, the power would decrease, the cost would decrease, and the performance would double every year, year after year, right? This is his original graph right there. He took it through 1975. We're still doing Moore's Law today. Now 12 months went to 18 months, went to 24 months. It's beyond 3 years now. We'll talk a little bit about that too. And of course, it's generally for large digital designs like processors, or it could be a GPU and the like, or a large memory. Now, if you think about what does that mean for something to double in power, same size, right, but double in performance, power goes down, cost goes down dramatically year after year. In 25 years, what you paid $1 million for becomes $200, right? That's why this is a miracle, right? You know, this march that the semiconductor industry has been on, and it's accompanied with a software march, and we're going to talk about that software revolution at the same time, is really what's enhanced the capabilities of the world. So functionality improves, year after year after year. But at 28 nanometer, we hit kind of a wall. And we had to go to a new type of transistor that we called a FinFET. And basically, in between the source and the drain is a kind of a three-dimensional structure. There's a vertical fin. And that meant we started to enter that world of mechanical electrical, right? And now at beyond 3 nanometer, we're going to go to something called a gate-all-around transistor, even more complex 3D transistor. And so as that's going on, as Yogi Berra, famous catcher for the Yankees for many years, you guys wouldn't know him, but he said the future ain't what it used to be. And so the cost is going up, is the moral of the story for electronics. We're no longer having the benefit of that doubling every year with the price going down. And you can see that trend here on the left-hand side as we kind of hit 7 nanometer out here. And the performance and power, though, continues to improve. And that's why cell phones not so many years ago might have been $350 and now sell for $1,000. So just some of the economics that are going on in place. So because of that, there's another trend that's happening, and I'm sure your professors talked about it, and it's called heterogeneous system integration that's going on. And that is, how do I take image sensors and analog and RF and combine it with GPUs and CPUs and with memory, and I do it by using something called a system in a package, or maybe I do it on a printed circuit board, or maybe I stack wafers. And that's the world of what we call is more than more, right? At the same time, Moore's laws continue to launch, right? But the cost per transistor is going up. So at some point, certain technologies like analog and RF will not scale like digital. And so therefore, we keep them at a larger node, but we start to integrate them differently. That's called system in package. It's called system design. Again, the reason Cadence a decade ago decided we needed to become an electromechanical analysis company in order to enable these types of stacked dies that have a lot of mechanical issues and material issues that we have to start to take into account with our design tools. That make sense? Let's just spend a minute on semiconductor manufacturing. You guys have a clean room here. It's actually pretty advanced. If you get a chance to work in it, you should work in it. I worked in semiconductor manufacturing. We had our own fabs at Harris. I learned so much about my design and when it failed than I ever learned about design when it worked, I can tell you. And I will almost guarantee you that if you don't know how to pray, you will learn how to pray when you wait for your design to come back. And when you try to test it, it is really agonizing. Now, there are 3 major advanced node companies doing semiconductors in the world today. The big dog, bar none, by a ton, is TSMC out of Taiwan. Samsung, they're also an IDM, so they create their own products, their own cell phones, if you will, lots of other things, right? But they also are trying to be more and more of a foundry. They are to a smaller extent. And then Intel's kind of going through the same transition. They're struggling a bit, right? Now, let's talk about the memory guys for a bit. The memory guys have their own foundries, right? So guys like SK Hynix, big partnership with Purdue, right? You guys are really lucky, really lucky. I know that it's going to be more packaging centric here, but everything I've talked about is the transition from Moore's law to more than more. So that's the right place to be going, right? That's where the puck is moving, right? And some of these memory companies, the big ones, of course, you see Samsung again, you see Micron, SK Hynix, large one in China called CXMT. Some of them share foundries, like Western Digital and Kioxia, which used to be Toshiba, actually share foundries because they're very expensive to build, right? Then there's smaller foundries. I think a buddy of mine, Tom Caulfield, the CEO of Global Foundries, was here recently, probably gave a talk. Companies like Tower and SMIC and UMC. And that's because most companies are fabless. And so they do all the manufacturing at a TSMC or at these other companies, right? And then there's some other companies that just have some specialized fabs of their own, like Texas Instruments, Harris. When I worked there, we did Analog Devices, Infineon, Bosch, and others. So that's the manufacturing landscape across the globe. Now, every advanced country is putting a lot of money into next generation manufacturing of electronics. Maybe for semiconductors, it may be for packaging, it may be for beyond package die. Whether it's China, whether it's the US with the CHIPS Act, we'll have to see how that morphs under Trump, but it will continue in some way, shape, or form. I can guarantee you that. Japan, Korea, Taiwan, the list goes on. India is going to build some large foundries very, very soon, in my opinion. Here's a picture of one of many TSMC aerial sites for their advanced node. In fact, this one, I think this building here actually does 3 nanometer right now. These are 4 to 5 football fields in length, each building, right? They're huge, right? Now, the more interesting part about it to me is there are no people. Why are there no people? What's the biggest reason there are no people? Yeah.
Like contamination.
That's exactly right. Contamination. I would also say for throughput, but contamination is one of the biggest ones. And contamination is not just what's in the air or what might get onto that wafer, but it's also vibration and other things like that are really problematic. Now, having said all of that, what you have here on campus and what you have the opportunity to experience is to go into that fab, put your bunny suit on, and really learn about how these are built. There are process engineers that are here to make sure these equipment keep running. But aside from that, they're not there. The whole front end, we call them cassettes, are all automated, and the whole back end, which is kind of how do you dice the wafers, and then how do you stack them, how do you test them, how do you package them, is all automated too. It's amazing how you can go into these huge facilities and not see any people. And that's why a fab like this, minimum cost today is about $20 billion. Generally, they're approaching now $30 billion per building. So think about that, right? Just to give you another number, in the past 2.5 years, TSMC has spent almost $200 billion building fabs. Fortunately, a couple of them are being built in the southwest of the US, one large one being built in Japan, right? So they're spreading it around a little bit, and one in Europe, right? Okay, let's talk a little bit about IC design. I'll get a little closer to home here. So let's talk about these guys, right? Somebody like, whether it's Samsung or whether it's Apple, right? Think about the problem they face, right? So every year they design a next generation processor using an advanced node, a new node that nobody's ever used before. Think about that, right? All the design tools have to be changed. All of the foundry processes are changing. And that chip has got to be ready by August in order for this to sell heavily through the holiday season. Every year. And beyond that, the biggest piece that has to come together is all the software on that new set of chips that are in this. I don't think anybody realizes just how hard that is. I realize it because I've been in front of the guy who runs that when he's been screaming at me because there's been a problem with our tools, right? On a brand new node where I don't even have enough data to adapt the tools in time. It's that kind of partnership that you're into. Very different from designing an airplane, right? Very different, right? And it's very expensive. Next generation, the M3, we'll show it in just a minute, almost $1 billion to design. Think about that. Here are some of the Cadence tools, right? Obviously, you start with some kind of system architecture and you do kind of gate synthesis at the digital level. That's what you see here with Genesis, and then you move into a net list. You're simultaneously working on your custom design it, whether using Virtuoso or Spectre. You're bringing in that IP I talked about for memory IP, PCI Express and the like, right? You're all integrating it into some large digital tool called Innovus for us. You do a whole bunch of sign-off, power sign-off, test sign-off, timing sign-off. The list goes on and on. At the same time, you're building the package in the PCB and trying to pull all this together. Now, Cadence, just so you know, more than 150 different tools. Many of them work together as solutions. 50 million lines of code. 50 million lines of code across all those tools. This is not for the faint of heart, right? Now, what this shows you is here's 65 nanometer, 13 million to do a design. And as you can see here at 5 nanometer, now we're working on 2 nanometer. The next Apple chip that comes out will be 2 nanometer at TSMC. 5 nanometer, we were at about $250 million. But there's 3 things that should catch your eye here. Where's most of the money spent? Verification, validation, and the biggest one is getting all the software ready. Right? And not the design of the chip itself. It's making sure that everything that's being developed at the firmware side, all the way through all the apps, come together and can be validated with the hardware simultaneously. So the latest M3 processor is built on TSMC's 3 nanometer technology using FinFET, still not using GAAFET. 2 nanometer will use GAAFET. 25 billion transistors for the M3. If you go up to the max, it's 92 billion transistors, right? Again, all of this designed in about 9 months, right? With all the software moving simultaneously, all on a brand new TSMC process, right? Cars, planes, trains, automobiles, there's no comparison in terms of complexity. But that pales in comparison to what NVIDIA does. Here you're at more than 200 billion transistors for the Grace Hopper chip, the GH200, right? Let's hear what Jensen has to say about the Grace Hopper chip. Now, he's talking to a good friend of mine, a buddy of mine from Stanford, John Chauvin. Maybe we can play the next one.
All of you in the audience probably do imagine there's a chip kind of like, like this. The chip that John just described weighs 70 pounds. It consists of 35,000 parts. 8 of those parts came from TSMC. That one chip replaces a data center of old CPUs like this into one computer. The savings of that one computer is incredible, and yet it's the most expensive computer the world's ever seen. It's $250,000 per chip.
So now you might know why Intel is in trouble. They rested on their laurels on processor designs for too long, let their manufacturing fall behind TSMC, and now it's a very, very difficult problem for them, right? At the same time, using ARM processors, that's what Apple uses as well, and NVIDIA as well. Other companies are attacking that laptop market simultaneously, right? Okay, let's talk a little bit about systems too. So as we move into that world of more than more, beyond Moore's law. So it's taking die, it's packaging them, it's stacking them, whether it's conventional or whether it's wafer level. It's how do I pull these together, logic, memory, and other functionality onto some type of next generation structure. Fortunately, Cadence is the leader here. We're, like your professor said, we're the leaders, fortunately, in custom and analog and RF design. We're also the leaders in package design, have been for more than 15 years, maybe 20 years, and increasingly the leaders in digital design, right? Of course, all those die, package die, then go onto a board, and board complexity has been skyrocketing. So if you look at the Apple VR system, the new one that came out last year, How many boards do you think are in that little system that goes around your eyes? Any guess? 15, too low.
100.
No, too high. 38. 38. Most of them are really small and are what we call rigid flex. They bend. They bend. But when you start to bend electronics using flexible connectors, a lot of bad things can happen. And reliability has to be really, really tested out. And at the same time, all that software is being integrated, right? So again, this is what this world is all about. Everything contains a lot of software, especially electronics. No comparison. F-35, by the way, they use a lot of Cadence products, 25 million lines of code. ADAS cards, over 100 million lines of code, right? Now, how do you get the software ready while you're designing the chip? And that's something called emulation and prototyping. So in effect, emulation allows you, as a design team, say at Apple or NVIDIA or AMD, by using Cadence's Palladium emulation system, you get a digital chip of your design before TSMC gets anything from your design, before they've fabbed anything. You have a digital twin of it, right? You can simulate it, you can optimize it, you can analyze it. And while that's going on, all of your software apps teams are porting their software to the digital chip, right? And this revolution is happening in every industry. Now, this Palladium Z3 is designed and built by Cadence. 5 nanometer TSMC designed by Cadence. We package it, we do the boards, we do the racks, the servers, all the analysis of it. This puppy costs about $1.5 million each. Large companies buy them by the dozens. NVIDIA just bought a couple hundred. No, they're just, right? These are FPGA based, right? So we don't do the FPGA, we do the system. But these two have to work together. So design teams and software development teams are always in sync, always pushing to get that iPhone ready, right? To get that GPU out on time, to get that laptop out on time. And remember, software verification and validation are the long poles in the tent. All right, I'm almost done. Just quickly, there are big E systems that are dominated by electronics. There are big mechanical systems like planes, trains, and automobiles that are dominated by mechanical. Increasingly, though, the brain and the nervous system of everything is a semiconductor and electronics, just across the board. Now, how about a data center? Cadence entered 2 new businesses in the last few years. One is we now do full digital twins of a data center, right? We're the only company in the world that can do it, right? From everything from the chips all the way through the entire chillers and the entire environment around it, a full digital twin that allows you to simulate and optimize it for energy consumption. 30% of an average data center is wasted across the globe. There's 7 million of them. They consume 3% of the world's electricity today. By the end of the decade, it's going to be 10% of the world's electricity that's being consumed. Why? For AI, right? Primarily, right? And so we've come out, and I told you that we're very concerned about carbon footprint, pushed by our customers to try to help them solve this problem. And this is NVIDIA's offering for the Cadence Reality Digital Twin platform that they're offering their customers so they can be more efficient as they make these massive investments across the board. So in summary, I think Cadence you might think of as a design company, but we're increasingly a solutions company. And whether it's looking at how the multiphysics analysis of a car or a data center unfolds, or even an airplane, but our core business has been kind of chip, package, and board. So with that, I can open it up to questions. I don't know how much time we have, but.
Not that much, I'm afraid.
Sorry.
We probably have a few questions. I get carried away too, so I'm not going to complain to anyone. It is a fascinating topic. So I have a couple of questions that were submitted earlier. I think we can afford the time to take a couple from the floor as well. So I'm going to, if you want to put up your hands if you have a question while I read one out here quickly. How does Cadence ensure its tools remain scalable and efficient with the increasing complexities?
Yeah, well, I will tell you that for advanced node design, the way we do it is we work with our bleeding edge customers, and you can guess who they are. And we work with TSMC because they are the big dog. And just the process, as a new process is being refined, like N2 right now for TSMC, we'll get 100 different PDKs within a year. The PDK are basically the device structures that we have to design our tools around in order for a company like Apple or NVIDIA or something like that to design at 2 nanometer. It's changing. We literally will get new device structures and tweaks 2 to 3 a week. Think about that, right? So it's painful. It's painful, but we have no choice. Scaling is probably the easier problem, but it's the process as it evolves that's the harder problem for us to catch up while our customers are on this march to get their next product out.
First of all, I'd like to say thank you for helping me ask the question. So you mentioned that semiconductors, the chips itself, are being launched every year, and they have to be more powerful, and the design is changing every year. But the software for it, like, I see it's not very different if you consider a iPhone 15 or an iPhone 12. Like, the end user software, it's more or less the same. So I feel that should software design be changed every year, or is that a process that can be eliminated?
So I can tell you, my thesis advisor, the same one that our CEO had, and actually the former CEO of Synopsys, we all shared the same advisor. His rule to us was the laws of physics never change, but you go back to school every year on software development. So I will grant what you said is true about software in terms of applications, and they may not change much as you move from one year to another year in terms of the porting to that chip changes a lot. All the firmware, everything changes a lot in order for that to work. But think about now AI unfolding, right? Think about Apple allowing you to do AI applications, or Microsoft or Google or others allowing that to happen real time on your next device, right? That's a pretty big software change, right? That's a great question, though. The software revolution will never stop, in my opinion, never.
If you could be quick. No, it's fine.
Yeah, it's fine.
You talked about simulating chips that still don't exist and are still not manufactured with another system. If that chip that is faster or will be faster or is expected to be faster isn't manufactured yet, how do you simulate that chip with lower computing power?
Well, how do we, let me put the lower computing power aside for a second, right?
Yeah.
So we actually create a digital twin of that chip, right, working with the customer, right? And that runs on that Palladium box that I showed you, right? And so all of the design teams basically build a 3D digital twin of the chip before they even think about manufacturing. And why? Because that process that I talked about is changing 2 to 3 times a week. It doesn't stabilize for 6 months. So they can't wait to start development after 6 months, so they have to work on a digital twin, and then we mesh those two worlds together really quickly. And that's why they're willing to pay $1.5 million just for one of these machines, even though they need a large number of them. Now, you did mention power. And what happens is that one of the biggest challenges is to do the low power network that's on these advanced processors and a lot of chips these days. So that aspect is really probably the second largest pole in the tent. If you look at kind of verification, validation, software development, the next one is power. So that's really a good question because power is a big problem.
Thank you so much.
My pleasure.
And,
Yeah.
give them a round.
No, thank you.